Hello and welcome to A Slice of Physics. This is the first of a series of videos that we hope will help enhance your understanding and performance in this physics course. The idea is to offload a lot of the lecturing information from classroom to these videos, which you can watch before you come to class so that you come prepared to do more hands-on activities and problem solving in class. In this first video, we're going to discuss numbers, units, and the scientific notation. We'll start with reviewing why it is very important to specify units while speaking of numbers. And then we will discuss some techniques that we use to deal with extremely small and extremely large numbers. Some of these techniques include prefix modifiers, such as kilos, milli, etc. And then we'll also discuss the scientific notation, another method used to work with very small and very large numbers. And finally, we will conclude with a discussion on precision of numbers as conveyed by the significant digits that they contain. Let's begin with discussing the importance of units. If I asked you your age, you might respond with something like 23. And if I ask you what speed you drive your cars at on the freeway, you might say 65. Each of these responses has numbers which represent quantities, and it's likely that I know exactly what you mean. I will assume that you are 23 years old, and I'll assume that you drive your cars on the freeway at 65 miles per hour. But what if your friend from the UK was visiting us? She might come to the same conclusion about your age, but for your speed, she might think you drive your car on the freeways at 65 kilometers per hour. See the problem? Let's take one more example. If I ask you how long it's been since you've seen your mom, and you respond with 4, I will immediately stop you and ask, for what? Is it 4 days, weeks, or months? The point is that units are important. And even though in our common language we sometimes omit them like we did in the first two responses, in this physics course it is crucial to specify units whenever you're speaking of numbers. Speaking of quantity, in science we often deal with extremely large and extremely small numbers. Here are a couple examples of large numbers. The population of the world, when I checked it, in November 2013, according to an online clock, was this large number. And the US gross domestic product was an even larger number. It was this value. How do we discuss such large numbers? Well, we use unit modifiers, typically prefixes. We would likely say that the population of the world is about 7 billion people, where people, in this case, is the unit for the population of the world, the number of people, and billion is the prefix that modifies that unit. A billion means 1 followed by 9 zeros, or 10 to the power of 9, and that comes from this above number by counting the commas. The first comma is 1,000 for 3 zeros, the second comma is 1,000,000 for 6 zeros that follow it, and the third comma is 1,000,000,000 for 9 zeros that follow it. So we can write this world population in another way as 7 times 10 to the power of 9 people, where the 10 to the power of 9, or a billion, is just a numeric representation of this unit prefix. And when it comes to the US GDP, we may say that this is close to $16 trillion. And I'm going to write the dollars here at the end instead of as the sign in the beginning, just to emphasize that in this case, the unit for US GDP is dollars, so there's our unit. And we have chosen to use the unit prefix modifier of a trillion to represent this very large number. The trillion comes from, again, counting commas. So we've got 1,000 for the first comma, million, billion, and trillion because we got 4 commas here. And so we can also write this as the GDP of the US is 16 times 10 to the power of 12 dollars, which in a more standard way might be written with the dollar sign up front 16 times 10 to the 12. Now unit prefixes also work equally well for small numbers. I'm going to clear up some room here and take an example of a very small number. For example, the width of a human hair is roughly 60 micrometers or 60 micrometers, where in this case meters is our standard unit and micro is our unit modifier. And micro stands for 10 to the power of -6. So the width of a human hair is 60 times 10 to the power of -6 meters. And the typical refresh rate of a computer screen is of the order of a few milliseconds. So here, seconds is our unit of time, and milli, which is 10 to the power of -3, is our unit modifier. So hopefully these examples show you how unit modifier prefixes such as million, trillion, milli, or micro can be used to deal with very large and very small numbers. Another technique we use to represent very small and very large numbers is the scientific notation. This is a standard way of representing numbers in a compact fashion, no matter how large or how small the numbers are. Let's take an example of the distance between the Earth and the Sun. Let's say the Earth is here and the Sun is here, much bigger than the Earth. And the distance between them is written in scientific notation as 9.296 times 10 to the power of 7 miles. So that's the distance between the Earth and the Sun. To understand what this number means, we are multiplying 9.296 by 10 to the power of 7, and 10 to the power of 7 is 1 followed by 7 zeros. So to expand this, we have to move the decimal places 7 places to the right. So let's start with our original number here, 9.296, and then move the decimal places 1, 2, 3, 4, 5, 6, 7 places to the right. And then we got to fill these extra spaces that we have created with zeros. So that's how many miles is the distance between the Earth and the Sun. And to understand this better, I'm going to add the commas after 3 places from the right and after 6 places from the right. And in common speak, we might call this 93 million miles. Or, as we wrote before, 9.296 times 10 to the 7 miles. Now this number contains the distance information. It also contains information about the level of precision we are conveying the distance to. So we're saying that the distance from the Sun to the Earth is 92,960,000 miles. In this notation, we're conveying this distance accurately to the nearest 10,000 miles, and we don't care about the precision beyond that, so that's why these last digits are filled with zeros. So the significant digits we have in this case is 4, and the 4 simply comes from the fact that there are 4 numbers that are contained in the scientific notation. Let's take a more common example. Let's say I ask you the distance from your school, which is here, to your home, which is here. Now for this distance, you might say something like 14 miles, or you might say 14.4 miles, and you will likely not say 14.436238 miles. The level of precision contained in this last answer is neither practical nor relevant. It's impractical for you to measure the distance between your home and school that precisely, so that's where the practicality comes in. And the relevance comes in from the standpoint that I don't care about this level of precision, so we will not typically say something like that, and we might say things like 14 miles or 14.4 miles. Written in scientific notation, the first response would be 1.4 times 10 to the power of 1 mile, and the second response would be 1.44 times 10 to the power of 1 mile. The number of significant digits in the first response is 2 because there are 2 digits here, and the number of significant digits in the second response, where it conveys a little bit more precision, is 3 because there are 3 digits here. In this slice of physics, we covered numbers, units, and the scientific notation. We started with discussing the importance of specifying units when dealing with numbers, and then we talked about how we deal with extremely large and extremely small numbers. These included prefix modifiers like kilo, milli, etc., and the use of the scientific notation. We wrapped up with a discussion of significant digits, which has to do with the precision conveyed by numbers. Thanks for watching.